That's a relief. Okay. I've got a few announcements to make today. I had a death in my family yesterday, so I wasn't able to get your grading done. I do have the key up on Blackboard. You can have a look at it, what that means. And I also wanted to have the test written so I could come in here and give you a few little hints. Means all that's going to happen Friday, so the test is moved to Monday. Okay. So, okay. By the way, if you're wondering, my first cousin passed away. He was only 27, so. God hates us. All right. Anyway. And it was cancer. I hate it when things just hang around. It was cancer. Cancer. Terrible. Anyway. So, let's talk about pretty things. Physics. All right. Are there any questions I should ask about the change in the schedule? So, things will come back on Friday. I will have written the test and I'll be able to give you a little bit more details on Friday. Yes?
Are we doing a crib sheet where, like, front and back?
Oh, it's an interesting thought. I'm cool with the crib sheet. I don't have a problem with the crib sheet. Let's do one side though, because there just aren't that many ideas.
Yeah.
All right. Okay. All right. Let's go ahead then and start talking about oscillations. So we left off last time, and we were talking about. Oh, that was cool. Last time was pretty cool. I'm sorry it didn't record, but we were talking about oscillations. And we solved the one-dimensional oscillator, and then we solved the two-dimensional oscillator, which was really fun. And we did an example of simple harmonic motion at the start. So I'm really sorry that did not record. Please get notes from a classmate, because that was good stuff. But we're going to move on today to damped oscillations. Okay, so in this case, the mechanical system we want to solve is a case where I have a block connected by a spring such that maybe here would be the equilibrium position for the block, but instead the block is over here at some location x. And let's just imagine that it's still moving in the positive x direction. Just to be most general, it can still be moving. And just to make our signs work out the easiest, we'll have it moving in the positive x direction. When that's the case, I've got to draw a free body diagram. I'm going to have weight here, and I'm going to have normal force. Again, it's going to be moving along a horizontal surface, so the weight will just balance the normal force. That'll be all the information you get out of Newton's second in the y direction. But there will also be the force from the spring, which is a restoring force here. And I'm going to allow there to be some air resistance. I'm still going to have that surface be frictionless, though. Because in the case of friction, that's actually an easier solution, and we want to move on. So we're going to have the case where I'm now going to include air resistance, air drag, lowercase f right there. All right. So in terms of Newton's second law, I'm going to concentrate on the non-trivial equation that comes from that, which is the x direction. And what I have is I have minus kx. Oh, I might be skipping this. Minus the force in the spring minus the drag force is equal to max. So now I'm ready to plug in. The magnitude of the force in the spring is kx. Remember, whenever I draw a free body diagram, the symbol represents the magnitude of the force. The direction is already in the arrow. That's why that minus sign is already there. So minus the drag force, which was, let's have the thing moving relatively slowly. I think that would be the most physically meaningful. And that's max. Okay, so our equation of motion is here, and I'm going to write it one more time. I'm going to put my max on this side, and I'm going to write that as mx double dot. Actually, let's put everything on the right hand side of the switch. So I've got mx double dot plus b dot x dot plus kx is equal to 0. Sure enough. Okay, so that will be our equation of motion. So we just need to find the mathematical solution to that equation. Now, this equation of motion is something that comes up in lots of different systems, lots of different places, and your author does a nice job of saying it. For instance, this is the same equation that you would get if you wrote an expression for the charge as a function of time on the capacitor in an LRC circuit. You get the exact same equation. Obviously, the constants are different, but mathematically, same relationship. So the solutions that we get from this equation won't just be applicable to this one physical situation. There's lots of other physical situations which something is oscillating but is eventually going to stop, meaning that it is damped, and this is the equation of motion for that system. All right. So let's do some math. All right, in order to solve this, the first thing I'm going to do is I'm going to divide everything by m. Great, and then I'm going to put some, rename some of my constants. This constant here, k over m, we recognize because we had square root of k over m would be the frequency of the oscillation if there were no damping. So that we will call omega naught squared, meaning that it's the angular frequency, and the naught means that for the free case where there's no damping, no other thing except for the spring, and angular frequency squared. All right. This guy, we're going to give an interesting name. We're going to call him 2 beta. And you're going to see why when we really get into the weeds on this mathematically. All right. So now my equation of motion, making those substitutions, x double dot plus 2 beta x dot plus omega naught squared x equals 0. All right, so this could also be considered our equation of motion. It's a little bit more mathematically friendly. And now the thing to do, because this is obviously a differential equation, is we're going to do a thing where we guess a solution. So my guess is going to be, well, I've seen stuff like this before. I need it to be a case where I have a function and its first derivative with respect to time and its second derivative with respect to time, and somehow everything adds up to 0. The only way that that can work would be if somehow these all were just functions of x and their constants could add up to 0. So my guess is going to be that x as a function of time, my solution, is going to be something times e to the something times time. All right, so in terms of its mathematical dependence, I'm just going to drop that front constant and say this is sort of the mathematical form for my solution that I'm going to guess. And then I'm going to see if it can work. In this case, x dot is r e to the rt, x double dot is r squared e to the, to the rt. Okay. All right. And let me now plug that back in to my equation of motion and see what I get. I get x double dot gives me r squared. I'm going to go ahead and call that e to the rt. I'm going to go ahead and call it x. Plus 2 beta times x dot, which is r times x. Plus omega naught squared times x equals 0. All All right, so if that holds, then my solution holds. So let me see how I can solve that. So I've got, let's divide out both sides by x as a function of time, which is fine. I can do that. And I'm left with 1 r squared plus 2 beta r to the 1 plus omega naught squared r to the 0 is equal to 0. And in order to find r such that this equality holds, and by the way, this equality has a special name. This is called the auxiliary equation for the equation of motion, which I made some substitutions. So it's really more the auxiliary equation of this form of the equation of motion. All right. So, have you guys seen this before? Oh, great. Okay, good. All right. So, quadratic formula time. I get my solution for r. It's negative b plus or minus the square root b squared minus 4ac over 2a. I always just have to write it out because when I skip a line, I make errors. So, okay. Negative 2 beta plus or minus the square root of 4 beta squared minus 4 omega naught squared all over 2. Okay. And r then must be equal to negative beta plus or minus the square root beta squared minus omega naught squared. Okay. So it turns out that my solution, my guess, actually works, but I have 2 possible values for r. So my actual solution is going to be a linear combination of those 2. C1 e to the r1t plus C2 e to the r2t. And I can go ahead and make my substitutions here. I'll have e to the minus beta plus or minus, so I can pull that out front. E to the minus beta t is going to be for both of them, times C1 e to the square, do I want to, yeah, square root beta squared minus omega naught squared t plus C2 e to the minus square root beta squared minus omega naught squared times t. All right? Okay. So that is going to basically be the solution. And then I'm going to analyze how the solution looks under different conditions. But this is our general solution. Okay. So let's consider the solution in all the sort of different physical situations that we might imagine. First, let's talk about the case where there actually was no damping. Let's talk about the undamped case and make sure that it works out. Undamped solution. Okay, so in the case that there is no damping, that means that B is 0, that means that B over M is 0, that means that 2 beta is 0, that means that beta is 0. So in that case, my solution just becomes e to the, C1, e to the square root beta squared minus omega naught squared. So it'll be I times omega naught. Okay? Plus C2 e to the minus I omega naught times t, where omega naught is really just omega for the undamped case. And that's the exact same solution that we got before. And we were able to write that in 3 other ways as well, if you remember. So it all checks out. That's the same solution we got before. Okay, now let's talk about the next case where we're going to call this the weak damping case. That means that beta squared is less than omega naught squared, meaning the beta is less than omega. So we're going to consider where beta is in its smaller realm, which is the case where it's less than omega naught. All right, so we will call this the weak damping solution. All right, so in this case, we are trying to consider the case where B would be among its small values. And what that means is that, I'm sorry, beta is small. That means that beta is less than omega naught. And if we want to consider the case where it's very small, we would say much less than omega naught. This will work in that realm. Okay. So in that case, we've got this square root of beta squared minus omega naught squared. But I've just said that beta is less than omega naught. So obviously the argument of this radical is going to be a negative number. So I'm going to pull that minus sign out as an I, omega naught squared minus beta squared. So now I've got a positive number under my radical. All right. And let's go ahead and give that a name so we can perform some substitutions and not have to write square roots everywhere. We'll call the square root of omega naught squared minus beta squared omega 1. Okay. So in this case, my solution becomes, I still have my e to the minus beta times t. And I'm going to give you guys a moment to complete that line. I'm going to complete it too on my own. Okay, that wasn't so hard. So, assuming I got it right, I had C1 e to the I omega 1t plus C2 e to the minus I omega 1t. You guys agree with that? Okay. And you know, still x is something we can actually measure, and obviously it's not going to have an imaginary component when we measure it. So this sum here must be real. All that stuff that we did last time is still going to apply to that expression. Meaning, what I mean by that is I can write it in those 4 different, but in terms of their meaning the same forms. So I could write this, for instance, in the amplitude phase angle form. So I'm going to use cosine with that, if I recall correctly. All right. And that'd be fine. And the nice thing about writing it in that form is that I see that clearly there will be oscillations and that the amplitude of those oscillations is this object out front multiplying that cosine function, which obviously is an exponential decay of the amplitude. All right. All right. So let let me go ahead and put a box around this. This is a pretty expression of the solution where I have weak damping. This is also called the underdamped solution. So we'll just weak damping. I'll go ahead and note here that this is going to yield the underdamped solution, which is here. Okay. Let's make a plot of that. So x is a function of time. I start out at A, and then I have some sort of a thing like this, where my amplitude is exponentially decaying towards 0. All right. Anything else I want to say about that? Just say the larger the beta, the quicker my amplitude goes to 0. And quicker the motion dies. Right? And we should also remember that amplitude was related to energy, total energy of the system. 1/2 Ka squared is the total energy of the system. So obviously energy is being leaked out through this beta term, which was that that drag force. So we're losing energy to the thermal motions of the air. So we're losing mechanical energy. It's turning into thermal energy. Okay. So next, let's talk about, we talked about the weak damping solution. Let's talk about the strong damping solution. So this is going to yield the overdamped solution. Okay, so what do we mean by strong damping? Strong damping just means that our beta is big. And what we mean by big is that beta is now going to be greater than omega naught. So I want to get back to my original form. So I've got this general solution there. So what I get from my general solution is x of t equals, let's go, I'll do that on our own real quick. Okay. All right, so here's what I got. I got C1 times e to the minus beta minus the square root beta squared minus omega naught squared times t plus C2 e to the minus beta minus, oh, sorry, plus square root beta squared minus omega naught squared times t. Okay, so there's our solution for the overdamped case, where in this case, C1 and C2 are now just real numbers because x will always be real. These exponentials are just real. They're just e to the negative a number times time. What else do I want to say about this? As t goes to infinity, we are going to just have this guy here who's got the even more negative exponent than the other. This guy here is going to dominate. So we sort of, at late times, this whole tail is just going to be an exponential dying tail, and that guy's going to take over. So in terms of what this resulting motion looks like of our sort of object on the spring, we get a something like that. Right? There is no oscillation at all, which is why those exponents are not complex. All right. And the weird thing here is that before, the bigger b was, the quicker the object sort of got itself to basically to rest at x equals 0. Here the bigger b is, the slower it does, because the slower it moves at all. It's got so much damping that it goes to that more slowly. All right. And so here's our solution. I should put a box around it. Not sure if I said anything else important except that this term dominates as t goes to infinity. So out here, you can well approximate the function just with the second term. All right. Okay, so let's talk about another possible case. We've talked about two cases for our general solution so far. We talked about the case where beta is 0. Now, omega can't really be 0 because that implies infinite mass. So we won't talk about that case. We talked about the case where beta is less than omega naught. We talked about the case where beta is greater than omega naught. And now we're left with one last case to talk about, and that's the case where beta equals omega naught, which will yield the critically damped solution. I'm off the page already. Okay. So in this case, I've got beta equaling omega naught. And if I come back to my auxiliary equation, I wind up with one equation for R. And the thing about let me show you if I let's go ahead and point out. So I got beta equals omega naught. I just get one value of R here. But that's kind of odd because I know I have to meet two boundary conditions. I have to meet initial location. I have to meet initial velocity. I mean, that's a weird mathematical thing where I've lost a degree of freedom, but my motion still has 2 degrees of freedom. So that's already a hint that that's going to mathematically be wrong, but that's okay. That's all right. So what we might guess is that from our auxiliary equation, we only get one possible value for R, so we'll only have one term in our solution, and that term will be constant times e to the negative beta was our solution times time. Okay. Now, we can plug that in as we had done, but I didn't show you for all the previous ones, to show that it does indeed solve the equation of motion and can solve the auxiliary equation, which is how we got them. But in this one, I think it actually makes sense for us to test the guess just because it's a wrong guess. And it's worthwhile to see why. So we're going to test it. We're going to test this guess by plugging it into our equation of motion right here. Okay, so plug it in there, and let's see what we get. I'm going to work it while you guys work it. Beta squared minus 2 beta squared. Everything did cancel out. Did everything cancel out? Did I make an error here? I don't know. What did you guys get? Did it meet? I think I have an algebra error. That's not. Can I see your work? What did you get? You got beta squared minus 2 beta squared plus beta squared. I know. Everything canceled out. Ugh, hate that. All right. Well, we'll have to figure out why that's not right then, because
it does equal 0.
It does actually equal 0, but that's all right. So it solves our motion. So I'll go back to the other point, which is can't meet all of our boundary conditions. How's that? Because I can't use 1 degree of freedom with a real number to meet both initial location and initial velocity. How's that? That makes more sense. Can't do it. Does that mean? So, I'm sorry, I made the wrong argument there. All right. So, my point here is that I have to meet my boundary conditions. So, I've got x naught is going to be equal to c1, right? But v naught, I have to be able to say that is equal to something and solve for a second constant. Here I can't, v naught isn't free to be anything. All right, so it's not the general physical solution. All right, it is a solution though, isn't it? Doggone it. All right. But it can't do what we need it to do, so we need to note that there is a second solution as well. The test actually turned out okay. Discrepant event for me. Discrepant, how do you spell discrepant? Good. All right, so the solution actually is a solution, but it's not a physical solution because I don't have anything that I can do to fit an arbitrary initial location and initial velocity. So what I notice is a second guess. And the second guess is that x is a function of time is equal to time times, let me see where I've got, okay, come on. times a constant. It's a different constant now, C2, e to the minus beta t. Okay, let's check that one too. And do you need the equation of motion back? That's going to be ugly. All right.
Oh.
All right. So that actually worked out for me, and I'm just going to show you. Why don't I just show you my work? All right, so I had this solution for x. That gave me an x dot, an x double dot, which I plugged in to my equation of motion. I went ahead and divided by c2 e to the minus beta t. And I got this expression where I got a negative 2 beta there, and a positive 2 beta there, and a beta squared t minus 2 beta squared t plus beta squared t. Okay, everything added up to 0. So that is also a solution. So there still is two solutions. They have the same exponential, the same exponent in their exponential. But there are two solutions as we needed. So that was exciting. So what we get is x as a function of time is going to be a linear combination of the two. All right. All right. And in this case, we still have C1 and C2 are both just real numbers now, not complex. And so both of these are going to basically die. Obviously, the first one dies faster. So in terms of as t goes to infinity, the first term will dominate. And we get x as a function of t. All right. So in this case, we call this the critically damped case because for this case, x goes to 0 and the motion dies fastest. Okay, so you can't damp it any better than that. Because if you tried to over damp it, then it doesn't actually die. It just moves super slow because of all that drag force. Okay, so those are all the solutions to the damped oscillator. So hopefully you realize what we have done is we have completely solved this system for every different possible physical variation we could think of. So we are done with that. So let's talk about the driven damped oscillator. All right. So in this case, my physical situation is I've got this object. This is x equals 0 back here. This is x. Free body diagram. I've got weight. I've got normal force. It's moving on a horizontal frictionless plane. So in terms of the y direction, I get trivial equation that will not relate to the x direction. I have the force from the spring. I have the damping force. And now I'm going to have a force that is a function of time that's applied by some external agent. So that's the sub ext. So this is kind of like, maybe that external agent is you. Maybe you've got an object on a spring that's moving there, and you're coming to come up and apply this force to it as a function of time. Maybe you're going to tap it every now and then, and your force can be written as a function of time. So this is something outside of it that's giving it pushes. All right. So in that case, Newton's second. The only important component is the x. So let's get our equation of motion here. I've got a force from the spring, which is negative, the friction, the drag force, plus the external force is equal to max. And I get F as a function of time. That external force is max plus the drag force, which is BV, plus the force from the spring magnitudes, that's kx. I could have made those substitutions over here, noting that's kx. And that lowercase thing is BV. Okay. Write that one more time. Force as a function of time is x double dot plus bv dot plus x dot plus kx. All right, awesome. So this is our equation of motion now. Your author does something kind of cute and divides everything by m, so that this first term here will be 1. And we're going to let the driving force divided by m be represented by a lowercase function of time. It's a little confusing because we use that for drag force as well. But what we get is our good old-fashioned equation. X double dot plus 2 beta x dot plus omega naught squared times x. Let me check it and make sure I haven't made any errors. All right. So this is our equation of motion. This is also our equation of motion up here, but this is the form that we're going to solve mathematically. And there's going to be some really cool math involved next. I mean, we're going to define the linear differential operator, which I don't have time to do right now. And we're going to do some pretty nice math. So next time should be fun, and I'll see you Friday. Hey, Greg. Oh, let me stop the recording.